All right, in this video, we're going to talk about the power rule. So we're going to talk about finding the derivative of any function that is f of x equals x to the n power. We're going to start off, though, actually talking about what happens when f of x just equals a constant, so just equals a whole number. Let's think. So the derivative is gives you the slope at any point along the curve. So it's a function in which you input an x value, and what you get out is the slope at that point, not necessarily the value of the function at that point. So say I want to plug in a point for x, and I want to know what the slope is on this curve. Well, no matter what I plug in for x, clearly, no matter where I am on this graph, the slope is just going to be 0. So the function here to give me the slope is just plug in x and get out 0. So again, that doesn't give me the value of the function. If I plug in an x, I get out the value, which is the constant. But if I want to know the slope, I plug in that value, and it will always just be 0 anywhere on that graph. The next polynomial that we'll talk about is a linear function. So let's just say we have a y equals mx plus b. I'll make another video about why the b isn't super important, but we'll come back to that. But in general, whenever you have a straight line, again, the derivative is the slope at that point. So no matter where we are on this function, the slope is going to be m. So say I pick a point, any point I want, x, and I go to that point, and I'm not asking for the value of the function. The value of the function is now changing. If I plug x into the original function, I'm going to get different answers. But my derivative is a function in which I plug in x, and what it gives me out is the slope. And no matter where I am on this line, the slope is m. So when I say linear function, you don't even really need to use any calculus. When it is a function of a higher degree, we have used the limit definition of the derivative, which again can be talked about in another video. And we've seen that when you have a quadratic function, the derivative is linear. And it's actually just 2 times x. And again, we've used the limit definition. We've also made tables and looked at how quadratic functions change. So those are 2 ways that you can back up this idea. You should explore both of those ways in another video. Additionally, when we have a cubic function, we know that that changes at a quadratic rate of change. We've seen that by looking at tables. We've also used the limit definition of the derivative to see that it becomes 1 less. So we know for sure that it goes down by a degree because that's how polynomials change. Their rate of change is always a function that is 1 less than the degree of the polynomial. And then the coefficient just comes from the exponent. Therefore, we can say in general, when we have f of x equals x to the n, we can take the derivative by multiplying n by the function and then taking x to the n minus 1. Now, of course, functions get far more complicated than this. Maybe there are coefficients, maybe there are other terms. There's other rules that you would need in order to find those derivatives.